Go ahead. Good morning, everybody. I am Gaetano Panagia. I'm a technical marketing engineer with Hamamatsu Photonics Europe. My talk today is about reinventing mid-infrared detectors, a breakthrough in sustainable technology for optical gas sensing. First of all, I want to give you an outline about my talk today. At the beginning, I'm going to cover general topics about gas sensing, comparing several technologies, optical and non-optical. Following up, I'm going to talk about optical gas sensing, and I'm going to mention a few methods that can be used to detect gases. And then in the end, I'm going to introduce Hamamatsu's sustainable technology in terms of mid-infrared detectors for the future of optical gas sensing. Brief introduction about my company. Hamamatsu was founded in 1953 in Japan. We have several subsidiaries in Europe, the closest one being in Urschen, close to Munich. The company commercializes and manufactures over 15,000 different products, including photonic components like the detectors I'm talking about today, but also light emitters, LED lasers, up to complete systems that can be used for biological research or semiconductor manufacturing. Diving into the topic of today, why do we need gas sensing? I identified basically three main reasons. The first one being safety reasons. In fact, there is some gases that may be explosive, like methane, hydrogen. Some of them can be toxic, like CO2, hydrogen sulfide, and some of them, like oxygen, can be both toxic and explosives. And we may want to measure them in certain environments like mines or oil rigs. Another very known reason to measure gas is environmental reasons. For this, we need to measure important greenhouse gases like, again, methane, CO2, but other gases as well, like NO2, SO2, or volatile organic compounds. And then this is an emerging field, the medical field, in which we measure CO2 through breath. And this is done because of monitoring of anesthesia or monitoring of reanimation. I decided to put here this table to compare a few different technologies that we can use to detect gases. Obviously, the choice of a specific technology really depends on the gas that you want to detect, because not all technologies are suitable for all gases. But I thought this could be useful whenever you have the possibility to choose. The first technology, very well established, is catalytic combustion sensors, which have a resistor and around that is wrapped up in a catalytic bed. What this sensor does is detecting combustion using a resistance measurement. Similarly, we have a semiconductor type that works in a similar way. In fact, there is a heated membrane, and on top of it, we have a metal oxide deposition. And what we measure here is the redox reaction that happens at the surface of the metal oxide. A different category is electrochemical sensors. In this case, we have basically an electrochemical cell. So you have a cathode and an anode and an electrolyte. And with this method, you're able to measure polar cells, polar molecules. So the molecule has to be electrically charged, or it needs to be ionized in order to be detected. But my talk today is going to focus about optical detection. And I'm going to present a few methods later. But first of all, I want you to focus on the comparison here. So price-wise, maybe optical sensing is a little bit more expensive than the other technology you can see in the table, but it is more accurate and has a faster response. So it's a very quick response. One of the main feature of optical sensors compared to the others, it's very long service life and low need for maintenance. These sensors, they do not have any moving parts. They cannot get poisoned. And once you install them, they need very little maintenance over time. Power consumption is also very low for this kind of detectors, which makes them ideal for battery-powered equipment, or in general for the deployment in remote locations where you don't want to go very often. And then last but not least, we have remote sensing. All the other detectors, non-optical detectors, they need to be in direct contact with the gas to work, while infrared optical sensors, they do not come in contact with the gas. Going a little bit deeper, I want to explain a little bit how infrared gas detection works. So we have a light source that emits low energy light. In general, we can use mid-infrared or near-infrared. And these electromagnetic wavelengths are absorbed by some specific molecules. And once this energy is absorbed, it's going to trigger some vibration, like the CO2 molecule that you can see there. What do we do practically? We use this Lambert-Beers law. So we measure the light that is emitted, and then this light is going to cross some sample, and then we detect the light that comes out of the sample. Doing so, we're able to measure what's called absorbance, and it depends on the specific wavelength that we're sending through the sample. The absorbance, which is also related to the sensitivity of our sensor in the end, it depends on three main factors. It is molar absorptivity, specific of the wavelength that we're going to send. We have the concentration of the compound that we want to measure, very important. So we're also able to measure the concentration of the gas. And finally, important for what I'm going to say in the following part of my presentation, there is path length. So the longer the path the light travels through the sample, the higher the absorbance, and the higher is going to be the sensitivity of our sensor. Today, I'm going to talk about mid-infrared wavelengths, but why do I focus on mid-infrared when the electromagnetic spectrum is so wide? There's three main reasons. One is we can achieve higher sensitivity in this wavelength range, mostly because the absorption peaks of many of the target gases is higher when we work with longer wavelengths. Second one, very important, selectivity. As you can see, going on the lower end of the electromagnetic spectrum, the gases are all crammed together, while when we move to longer wavelengths, the absorption peaks are more spaced apart. This means that we have less cross-sensitivity towards gases when working in mid-infrared. And the third reason is a lower impact for water absorption. So we have several absorption peaks at the shorter wavelengths, but moving to the mid-infrared, water is absorbed less, and this makes our measurement independent from humidity in the air, for example. Going forward, I'm going to present a few methods that we can use to detect gases. And I want to make sure it's clear that Hamamatsu is not manufacturing gas sensors. We are providers of components. So you can see the LED and the detector in this case, but not the whole sensor. The most simple and inexpensive gas detector is a non-dispersive infrared detector. It is quite simple. Again, it is composed by a LED or a broadband light source on one side. Then you have a gas chamber. And on the other side, you have a detector, which can be a quantum type or thermal type. And I'm going to explain the difference a little bit later. In front of the detector, you have a bandpass filter, and the passing band of the filter needs to be the same absorbance wavelength of the gas we want to detect. So, for example, in this case, we have CO2, which absorbs in the mid-infrared at 4.26 micrometers. So the bandpass filter is going to have a similar passing band. With just a little modification, our system can become faster and achieve a higher selectivity. And the simple modification is using a laser instead of a LED or a broadband lamp. In this case, we have a tunable diode laser spectroscopy system. The laser, in fact, emits higher output power, making the system highly sensitive and much faster. And we make it also more selective because the laser has a narrow emission bandwidth. We don't need, in this case, any bandpass filter. And the sensor can only be quantum type. And again, this is related to the speed of the system. And we're going to see it a little bit later. Cavity ring down spectroscopy is the third system, the third method that I'm going to present. And it is quite similar to the previous one with a clever addition. The addition is three mirrors that create a cavity inside the gas chamber. So again, we have a laser that emits a short high power pulse. The light enters the chamber and starts bouncing off these mirrors while being read out little by little by the photodetector on top. This increases the path length that the light has to travel, and in turn, it increases the absorbance and the sensitivity of our detector. It is a very fast method. We can have a long path length while keeping the design compact. It is fast and highly selective because we're using a laser again. What happens, as you can see, is that whenever the gas is not in the chamber, the energy measured by the photodetector decays little by little. But whenever we have a gas in the chamber, then the decrease is going to be steeper. So then we're going to be able to detect a concentration of CO2 in this case. The only thing we need for this is a fast detector. So we cannot use any kind of detector. And this is why in this table, I want to present what are our options in terms of detectors when we do mid-infrared measurements. On one side, we have thermal sensors, namely thermopiles or pyroelectric detectors. These are very good detectors because they are wavelength independent. So their detectivity is the same no matter what wavelength you're using as an emission. And they are fairly low cost for your system. The main drawback is that the detectivity in general is lower than when compared to traditional quantum sensors. And most of all, their response is fairly slow. We're talking about milliseconds against nanoseconds that can be achieved by quantum sensors. When we move our attention to quantum sensors, we see that we have lead sulfide, lead selenide, and mercury cadmium telluride detectors. These achieve a higher detectivity with respect to the thermal sensor, but while the first two have a limited wavelength range, which stops at about 5 micrometers, and a slightly slower response, the MCTs have a very long wavelength range. They have a very high sensitivity. They need to be cooled down very often, and this makes their cost to go a little bit higher. But there is an issue that these traditional quantum sensors share. And the issue is the presence of heavy metals inside of the material. We're talking about lead, we're talking about mercury, we're talking about cadmium, that at some point in the life cycle of the sensor is going to end up in a landfill and is going to cause environmental pollution. There is a European directive that restricts the use of this material in sensors as well, but these specific ones can be manufactured and commercialized due to some exemptions, temporary exemption to this ROS compliance directive. This means that they can be used temporarily up to 2027 or 2028, according to the specific application they're going to be used into. And this is the main reason why at Hamamatsu, we started thinking about alternative materials for detecting mid-infrared wavelengths. And our engineers are pioneers in the development of sensors using indium arsenide antimonide material. This material is totally comparable to MCTs in terms of wavelength range. We have products that are highly sensitive up to 5 and 11 micrometers. They work at room temperature. They can be cooled down, but they also work at room temperature. They have a fairly fast response time that makes them suitable for cavity ring down spectroscopy. They're available in several different packaging, like SMD packaging, for example, or the TO can that you can see here. And most importantly, they do not contain any of those heavy metals. Of course, every technology has their drawbacks, right? So I'm going to present with a few challenges that our engineers had to face whenever developing these sensors. One of them, maybe the most important, is limited detectivity at room temperature. This was caused by high background noise and poor Shockley red Hall lifetimes. What that means is that whenever a photon hit the crystal, there is an electron that is created, and this electron need to be read out by the circuitry before it is recombined. And it was very difficult because the electron was recombining before being read by the circuitry. Another challenge is we could not achieve large crystals with high quality. So this limited the active area of our detectors. And our engineers came up with a very clever solution. Since we could not grow large crystals, we started growing several small crystals and we connected them in series. In this way, we could have a large active area without the need of any focusing optics. And we solved the problem of limited detectivity because now the electron didn't have to travel very far before being read. Another challenge was high temperature sensitivity. This means that basically, whenever environmental temperature was changing, then our photosensitivity was also changing by about 1% per centigrade degree. With our new back illuminated fabrication method, this improved a lot, and now we're able to have a photosensitivity of about 0.1% per degree Celsius. This all talk then comes to the presentation of the latest detector that we released, which is this P16702. This is a detector with high sensitivity up to 11 microns and with a high cutoff frequency at 100 megahertz, and that integrates a transimpedance amplifier for easy integration. This specific detector is thermoelectrically cooled, so our circuitry is also capable of keeping the temperature of the detector